In this video, we'll discuss MOSFETs as black boxes and some little introduction about these devices. The slide courtesy for this video is for Professor Lundstrom from Purdue University. So to start with, shown over here is the side view of a MOSFET. Okay, a simple MOSFET. What you see over here is a simple p-type silicon substrate. Okay, and then you have these diffusion regions, the source diffusion region and the drain diffusion regions. These are heavily doped regions. Okay, now this is p-type bulk silicon substrate, which you can easily get from somewhere in the market, and then you have these heavily doped n-type source and drain regions, and here somewhere in the middle you have an oxide, and then on top of that you have a gate. Now it's very important to understand why they are named as such, as source and drain. So source, by its nomenclature, it means that it supplies the carriers, okay, for the conduction of current. And drain, what it does is that it simply collects those carriers that are coming all the way from the source. Okay, now excuse me. Now in order for current to sustain or to exist in this region, this portion of this transistor should have enough carriers so that current can flow from source to drain, and that is something which is brought about by something known as field effect. So we'll talk about the physics and working of MOSFETs in great detail in the coming lectures, but the idea of this video is just to introduce these devices to you. Anyway, so this is the top view of this MOSFET. Okay, the same structure. So this is the side view or the front view. Now the same structure we are seeing from the top. Okay, in this direction. Okay, in this direction, vertical direction. So what you see is, here you have a gate. This is the layout of a gate. These are the source and drain contacts. Okay, often you see that there may be multiple source and drain contacts, and that is to minimize the contact resistance. Okay, so you have multiple of these contacts, and this is the width of this device. So the length of this device would be right what is underneath the gate. That would be the channel length. Okay, so that is a little bit about the architecture, or the structure of the MOSFET. Okay, now as a circuit designer, we don't bother about what is inside the MOSFET, how does it work. You simply use it as a black box. Okay, from a circuit designer point of view, all that matters to you is that you have the device characteristics, or you have a model for that device, and that is what you use in your design tools, and you carry out the design. But what is important is that all you know is that how does current vary for some applied set of voltages between any two nodes. Okay, that is all that is given to you, and that is all the information that we use as designers. There are a lot of there's a variety of transistors that is available in the market, and that is being researched on, okay, in the state of the art. So you have this very well known, very common kind of a transistor called the MOSFET, right? Metal oxide semiconductor field effect transistor. Then you have the SOI MOSFET, or silicon on insulator type MOSFET, or you may be using a Schottky barrier FET, a FinFET. Okay, in which you have the channel in the form of a fin, and the gate is on its three sides. And then you have a modulation doped FET, or a HEMT, high electron mobility transistor. You may be having a bipolar transistor, a junction FET, an HBT, or a band-to-band tunneling FET. So these are the different variety, and there are even more beyond this, different types of MOSFETs that people are working on in the industry as well as in the academia. So if time permits, we'll try to cover as many as possible from this list. Now, so in the previous slide, I showed you a simple cartoon of a MOSFET. That was not how MOSFET actually looks like in reality. So this is a zoomed SEM or TEM picture of a MOSFET taken from Texas Instruments. So you see that these are not as well behaved in nice corners, and in particular perfect shape, these structures. You may be having slight deformations or some kind of tapering somewhere in the structure, and that is how these things are in reality, and that's why you see some more real type effects. So at this point you see this is the source contact, okay, and then you have the drain contact. So this, I mean, this is the metal contact, so this reaches all the way through this via hole, this hole, all the way to the source diffusion region, similarly to the drain diffusion region. This over here is the gate, okay, and this just minor, this small thing that you see over here, right, this is your oxide. It's very thin, right, underneath the gate, and this is the channel, just this much is the channel. And then you have, this is the usual semiconductor or silicon bulk, right, and everything else other than this is the oxide. These are different type of field insulating oxides, because you don't want the transistors to interact or get connected with neighboring devices. Okay, this is used for insulation or isolation. And this is this symbol that is used for a MOSFET. So you have the source here, you have a drain, you have a gate, and the body. I'm sure you must have come across this kind of a symbol before. Now MOSFET, since it has three terminals or maybe four if you consider the body, then it can easily be used in a two-port network. Okay, this is how you can use it as a two-port network. So gate and source, these two terminals form one port, and then drain and source, they can form another port. Okay, and even this kind of a topology, a common source topology, is often used to find out the characteristics of these devices. So the characteristics, so the most commonly used or the most commonly looked at, for the sake of understanding or for the sake of evaluation of these devices, they are called IDVG or IDES VGS characteristics at a fixed VDS. So in this case, current is seen as a function of gate to source voltage for some fixed VDS value, and these are called transfer characteristics, because we are measuring IDS or the drain to source current as a function of gate to source voltage. So output characteristics, output quantity as a function of some input quantity. Therefore, you have the transfer quantity, the transfer characteristics. These are called transfer characteristics. And on the other hand, if we measure or if we see ID or drain current as a function of the drain to source voltage, ID is after all an output quantity, and the output voltage VDS is also an output quantity. So output versus output. So this is an output characteristic for a fixed gate to source voltage. Okay, just keep this thing in mind, because this is something, this is the bread and butter of those people who work on semiconductor devices, these equations. Anyway, so now let's talk a little bit about a resistor. How do the characteristics of a simple resistor look like? An ohms resistor. Okay, so we very well know the relationship in case of a resistor, how I and V are related, given by this well-known Ohm's law. Okay, and these are the characteristics of a resistor. So current increases or decreases linearly with the voltage that is applied across its two terminals. Fine, it's very simple, something that goes back to 10th, 11th or 12th class. So as and the slope of this characteristics, okay, that is determined by the value of the resistance. So higher the value of the resistor, you will have a smaller slope. I mean, you will be having this kind of a characteristic. Okay, and if you reduce the value of the resistor, maybe you will have a more sharper characteristic given by this one. Keep this thing in mind. Okay. Okay, next, so these are the IV characteristics of an ideal current source. Okay, we have a current source, a perfectly independent current source, an ideal one. So the characteristics would look something like this. So current doesn't vary at all with the voltage that is applied across its two ends. Current will be fixed no matter what is the voltage applied, whatever is the value of V. So I will be given by I naught. I naught could be any value. Okay, now this is a hypothetical one, because in reality we don't have ideal current sources, but for the sake of understanding and for the sake of illustration, we are having it here. So this is the characteristic. A flat line on an IV characteristic represents an ideal current source. okay, which doesn't change with the voltage that is applied across its two ends. Okay, so now we know the characteristics of a resistor, we know the characteristics of an ideal current source. Now look at the IV characteristics, the drain to source voltage and current for a MOSFET. This is what it looks like. Something like a combination of a resistor and a current source. So within this region, so we are plotting ID versus VDS. Okay, ID versus the voltage applied across VDS for a fixed value of VGS. We are not changing, we are not sweeping VGS. Let's say VGS is fixed to some value, and then we are trying to measure the current that flows from this terminal, and what is the voltage across these two terminals. So that is given by this kind of a characteristic. Now this region, okay, this does look like a resistor, as I just mentioned previously. So this is a simple resistor behavior, and this is an ideal current source behavior. Okay, but note that the slope of this resistor, so this is fixed for a fixed given voltage, given gate voltage. If we change the gate voltage, then the slope of this resistor may change. So you can say that this is a gate voltage driven or a gate voltage controlled resistor. Okay, and since the current changes linearly with the applied drain to source voltage, this is also called as the linear region. Okay, earlier back in the days of vacuum tubes, this would also be known as the triode region, but in this course we would be mostly referring to this region as the linear region. And in this region, which is flat, the current doesn't increase anymore beyond this point and gets flattened to a value. It's called saturation region. Okay, and again the level of the current, if you apply a higher gate voltage, the level would rise. If you apply a smaller gate voltage, the level would reduce. So this is a gate controlled current source. The value of this current source, this is after all a current source, right, an ideal current source in this region, and the value of that current I naught in this case is determined by the gate voltage. Okay, so this is, but note that this is an ideal case. Okay, this is not how in reality a MOSFET behaves. Now let's go back to this kind of a structure where we have a current source, an ideal current source here, and in parallel to it we have a resistor. That is how in reality a real current source looks like. Okay, you have a current source here, and then you have a resistor in parallel. In ideal case, this would be an open circuit. Okay, so you only have an I naught here, but in reality you will have some finite value of R naught. And if you want to plot the characteristics of this structure, the terminal characteristics, so this is how it would look. So we have V as the voltage applied across these two terminals, and if let's say we didn't have I naught here, if I naught was 0, then we would simply have the characteristics of a resistor given by this thing. But note that this wouldn't be at this point, it would be starting from here, right? It would be centered at this point at I is equal to 0. Okay, because for V is equal to 0, I would have been 0 for a resistor. But since we are also having a current source, an independent current source of value I naught in parallel with this resistor, so we'll just simply raise that thing. We'll give it a DC offset, or we'll raise those characteristics to this point, and this point is I naught from this point. Okay, so these are the characteristics of a current source which is real. It is not ideal because it has this R naught associated with it. If this R naught was infinite for this structure, if this R naught was infinite, then what you would see is this dashed characteristic here. Okay, which would correspond to your perfect ideal current source. All right, let's move on. Now these are the IV characteristics of a real transistor. Okay, of a real transistor. This is how it actually looks like. The dotted one represents how we try to imagine it as a linear resistor in this region and an ideal current source in this region. Okay, but this is how it actually looks like. There is of course some tapering, some departure from this kind of characteristic, and we'll talk about it. But anyway, the definition, so this region is anyway referred to as a saturation region. Okay, and this region is referred to as a linear region. Keep this thing in mind, and please keep this thing in mind that this is ID versus VDS. So far we have only discussed the drain to source current versus drain to source voltage, okay, for a fixed VGS. And in this case the VGS is given by some VGS1 value. It could be 1 volt, 1.5 volt, 2 volt, whatever. Okay, now so this is one fixed VGS value. If we apply, if we plot these characteristics for multiple VGS values, then this is what we would look like. Okay, what it would look like, we'll have one characteristic here for one VGS. As you increase VGS, you'll have another characteristic. Another VGS will have another different characteristic. You keep on increasing VGS, you'll get a different, you'll get all this family of curves, family of characteristics. These are called the output characteristics. Okay, on the x-axis we are only sweeping VDS, and once we have swept VDS, now we change VGS. Okay, then again sweep VDS, we get this thing. Again we change VGS, and then again sweep VDS. Sweeping we are only VDS, but for VGS we are giving a few different multiple values. Okay, now a few interesting things to note here. Number one, so this tells you this point, this inflection point, it tells you the saturation voltage at which which demarcates, which differentiates the region, the linear region from the saturation region. This is called the saturation voltage, VD-sat. Okay, now VD-sat may not be the same for all of these curves. For this one you may say VD-sat is here, and then for this VD-sat is here, and it may come more and more towards the left hand. Okay, we'll talk about that in the subsequent lectures. And as you keep on increasing the VGS, current increases, right? As you keep on increasing VGS, you'll see the current for each curve is increasing. After all, the y-axis does represent current only. All right, and so this is the linear region, this is the saturation region. Just keep that in mind. Now we'll talk about transfer characteristics. What do we mean by that? We are plotting current or drain source current as a sweep against VGS. Now we are fixing VDS. Okay, we are fixing VDS, but now we are sweeping VGS. So in this graph or in this picture, we have the characteristics, the transfer characteristics for two different VDS values. Okay, so for one VDS value, the lower one, we have this characteristic, and for an increased VDS one, we have this one. Now remember the lower VDS in the previous case. Okay, the lower VDS, for example this one. Okay, basically it is this figure that is plotted in the next slide. So if you plot this thing, this is the fixed VDS value. If we choose this value and we see the different VGS values and we plot the current, what we would see is this thing, this dash thing, right? So just try to imagine this thing. So we are fixing VDS and we are seeing what are the values of current for different values of VGS. Okay, what we will see is this thing. Okay, so this is called the linear characteristics, right? So linear characteristics, because after all this is linear region behavior, right? Anything to the left of this VD-sat is linear region, to the right of the VD-sat is saturation region. Now if we take this high VDS case, we are choosing a fixed VDS case and we are seeing how current changes with VGS, because these different curves are for different VGS, and what we'll see is this kind of a plot. Okay, so this is for saturation. This IDS VGS is for saturation case, this is for linear case. And this point where the current starts to rise, this very well known, very famous point in applied VGS, this is called the threshold voltage. So before threshold voltage, it looks like the current is zero, but in reality it's not zero. But let's say we have some very small current, but as soon as you reach VGS, or you reach VT or threshold voltage, the current immediately increases. Okay, now since these are for different VDS values, so you'll have different behavior for current for different applied VDS voltages. Okay, now MOSFETs generally are used for two major applications. One is where it is used as a switch. Okay, a switch is nothing but something like which opens and closes based on some external stimulus. So that stimulus is provided by the gate. So you change the value of the gate voltage, you either connect it or open it. So this is called a switch. Okay, and the other application is where it is used to amplify your signals. So you have given an input of a relatively small magnitude, a small signal at the input, and what you get at the output is a magnified one or an amplified one. This is something which only a transistor can do. If you have a combination of resistors and you give some input small signal here, you would, no matter what combination you try, you will not get an amplification at the end of a network of resistors. Why? Because resistors are not gain providing devices. Okay, but a transistor in itself is a gain providing device, and we'll talk about that. Okay, now this again, going back to the initial cartoon on n-type MOSFETs. So this is an n-type. Why? Because the channel that forms that sustains current here is of n-type, or electrons, right? So source, it sends electrons, and those electrons reach the drain, and within the channel it's the electrons those carry the current, even though the substrate is p-type. Okay, and how current forms or how the channel is formed is called by a field effect, and so it depends on whether we have applied strong VGS or strong gate to source voltage which is greater than threshold voltage. In that case the channel gets inverted and we have a current. So we'll talk about all of this MOSFET operation in really thorough detail. For now you'll just have to bear with me because I'm just introducing this topic. Okay, so this is an n-type MOSFET with a p-type body, but the channel is n-type, so therefore the MOSFET becomes n-type. Okay, so on the other hand, we have a p-type MOSFET for which the substrate is n-type silicon. Okay, in which the substrate is doped with donors to make it n-type, and the source and drain regions, they are heavily p-type doped, and therefore the current has to be sustained by holes, right, which are p-type, and therefore the MOSFET is called p-type. Note that in this case the applied biases for turning this device on are opposite to what you see here. So the gate voltage has to be less than a threshold voltage for channel to form so that current can flow. Just like in this case we have the gate voltage that should be greater than the threshold voltage for channel to form and current to flow. We'll talk about all of these things in huge detail in the subsequent lectures. Now let's talk about MOSFET device metrics. So what we have here is a family of curves, the output characteristics, right? ID versus VDS. So from these characteristics, we can obtain a lot of device metrics. For example, let's start with this one. So we can see that this region is linear, okay, and if we observe that this behaves like a resistor, okay, and the value or the slope of this one should give us a finite value of resistance. This is called the on resistance. Okay, note that it corresponds to the highest applied gate voltage curve. This is the highest applied gate voltage curve, right? And the slope of this in the linear region gives us the on resistance. Okay, and then you have the saturation region. This is the saturation region. Ideally this should have been a flat one, right? But in reality it's not flat due to something which is known as channel length modulation. We'll talk about that. So therefore this behaves like a real current source, right? As we mentioned in some slides earlier, that this is not an ideal current source because it has a finite slope, and the slope for this one, this corresponding to this one, should give us what is known as the output resistance. Okay, but note that all these characteristics are for the highest applied gate to source voltage, which is given by VDD. Okay, okay, and this current, which is the highest, the maximum current for a maximum drain to source voltage, maximum gate to source voltage, this is called on current. All right, this is the on current of the device. And finally, if we see how current changes as a function of gate to source voltage as you go in this direction, the derivative of that is called as transconductance. So maybe transconductance is not as obvious from these curves. So for that we'll have to plot current as a function of VGS, okay, because we want to see the transfer characteristics, and then from that we can understand the transconductance. For example, in this case, so this is transfer characteristics, ID versus VGS, right? So we see that this is for the linear case, as we mentioned earlier, This is the linear case. This is the saturation case where VDS is nearly VDD, or the applied or the available supply voltage. Okay, and this is the on current, ion maximum current. It's the same current. This current is the same as this current. Okay, and this point, if we extrapolate these characteristics back to the VGS axis, this intersection point, this gives you the threshold voltage. Now, since these have two different threshold voltages, so one for the linear and one for the saturation region, so we call it VT lin and we call it VT sat. All right, now this interesting region, it does look like as if there is no current here. The device here in this region is off. In reality, there is some finite current, because if we plot these current characteristics in log scale, so if y-axis is plotted in log scale, what we'll see is something like this thing. We'll have this behaving in a linear fashion. The current in the off state, something to the left of the threshold voltage, goes linearly as a function of VGS in the log scale. So something that changes linearly in a log scale, what does that tell you? That tells you that the current is changing exponentially with voltage. Okay, in reality, it is changing exponentially. So it in a log scale representation, it does look like it is changing linearly. What it means that it is changing exponentially with voltage. So you see that even though current is low, but it is not actually zero, and it changes heavily as you keep on changing the voltage. Before you reach threshold voltage, beyond this, the current starts to behave linearly. Okay, because this is log scale, it does look like it is flattening, but if you go back to the previous plot, you see the current is changing linearly. Okay, and there is one more phenomenon. Dibble will talk about this in the subsequent lectures, because this needs more attention. Okay, so to summarize, if we have a set of characteristics, measured characteristics of a MOSFET, so all these quantities you should be able to find out. You should be able to find out the on current, the off current, the subthreshold swing. By the way, let me go back to subthreshold swing. I missed it. So what is subthreshold swing is how much of current does change for applying any voltage in the x-axis. For example, let's say that the current here is 1 milliampere, for example, at this point. Okay, if this is 1 milliampere and the current here is, let's say, for example, 0.1 milliampere, or let's say 100 milliampere. Okay, so it's changing from 1 milliampere to 100 milliampere as you go from this point to this point. And how much is the voltage that you have applied for changing that current? Okay, that gives you the slope. So ideally what you want is that you should have to apply minimum current for changing this slope. Ideally you want these characteristics to be vertical as possible, as sharp as possible. Okay, so that you can turn this device off. Otherwise it will take you this much voltage. You have to go this much all the way from the threshold voltage to turn the device off. Okay, so this is something which is of interest to those people who work on low power devices, okay, to reduce the power consumption and all those things. So that is given by the subthreshold slope, and the unit for subthreshold slope is millivolts per decade. Yeah, how many millivolts do we need to change the current by a decade? A decade means 10 times. So 1 millivolt to 100 millivolt means 2 decades, right? So 2 decades, for example, this voltage was 10 millivolts. So it would be 10 millivolts per 2 decades. That's just a hypothetical number, okay? In reality, in all MOSFETs, the minimum value for subthreshold slope is 60 millivolts per decade, and we have it in the subsequent lectures. Okay, as I was saying, so also you can measure all these characteristics: VT lin, VT sat, R on, VD sat. So all these characteristics you can find out if you have a set of IDVD and IDVGS characteristics of a MOSFET. So what I would suggest you to do is go to Google and try to find out the IDS VDS or IDS VGS characteristics for any device, any MOSFET. Okay, use any source, any literature, any journal, or anything you find, and try to find out these characteristics from these metrics from those characteristics. It would be very interesting, and maybe let me know what is the value of subthreshold swing that you find out. Let me know what is the R on you find out. Okay, I'll stop here and we'll continue in the next video. Thank you.